Once again, good morning, good afternoon, and good evening, everyone, to everyone present here. Welcome to today's webinar from Multicoreware on Efficient AI for Tomorrow, Techniques for Optimizing Neural Network Ops on Accelerators. So before we proceed, I hope I'm audible and loud and clear, and I hope you can see me. So my name is Srinivas. I'll be the moderator for this session for you all today. Thank you all for joining in. We have an exciting speaker who will share their expertise on this important topic. But before we dive into the webinar, let's quickly go over the agenda. The webinar will happen for 45 minutes. The presenter will continue their narrative uninterrupted until the end of their presentation. Once the webinar is over, we'll have our Q&A session that will happen for 15 to 20 minutes. You may pose your questions in the chat box and we will try to answer them in the meeting given time. The window for the question and answer session, the chat box will remain open till the end of the webinar, and all of the questions will then be collated and sent to you in a couple of days' time, along with the recording of the event. And finally, in order to maintain the order, the webinar will be in listening mode only for the audiences. So before we move on to the webinar, I'd like to give an industry outlook on the topic that we have today. So artificial intelligence is undoubtedly an important tool to transform the technological landscape as it continues to develop. And the AI accelerator as such enhances the performance of the Internet of Things, IoT, and robotics. So AI accelerators also boost these applications by driving complex algorithms and processes such as machine learning and deep learning, and such as the AI ML space in of itself is witnessing a rapid evolution with increasing demand for efficient AI solutions. As companies strive to extract the maximum potential from these AI models, the focus has shifted towards enhancing efficiency, performance, and scalability. Efficiency in AI is gaining performance prominence as businesses seek to optimize resource utilization and reduce operational costs. So by leveraging these specialized hardware accelerators such as GPUs, FPGAs, or ASICs, companies can significantly boost the computational capabilities of neural networks. This, of course, enables faster inference and training times, enabling real-time and large-scale AI applications. Optimization techniques such as model compression, quantization, and pruning are gaining traction. These techniques aim to reduce the computational complexity and memory footprint of neural networks, enabling efficient deployment on resource-constrained devices and accelerating inference speeds. With this, let me now welcome our speaker for the day, Nadia Singh-Godin from Multicoreware. She is the Senior Engineering Manager of Platforms and Compilers. Nadia, are you there on the meet?
Yes, sure.
Yeah, hi, Nadia. Yeah. So Nadia demonstrates exceptional proficiency in enhancing the throughput of computer vision and neural network operations by means of optimizing their execution on GPUs, DSPs, and NPUs. And her skill set is on the fusion of expertise in hand tuning techniques and an intricate comprehension of hardware architecture. Let me now proudly welcome her. And now for the most important part of today's agenda, I'd like to welcome Nadia to take over the session and present the webinar.
Thank you all for joining this webinar today on Efficient AI for Tomorrow. I'm Nadia, working as Senior Engineering Manager at Multicoreware. Today, I'll be briefly covering the fundamentals of optimizing neural network operations or pipelines for the target accelerators. And I'm going to really cover some of the fundamental approaches that Multicoreware follows for optimizing any given software for the target accelerators. Before I proceed, I would like to give a quick overview of our company. Multicoreware was founded in 2009 and is headquartered in Silicon Valley with a strong global presence, including sales and delivery centers in the USA, Europe, India, and China. We are now 370 plus with a diverse group of engineers specialized in machine learning, artificial intelligence, and domain experts with deep knowledge across various industries. Multicoreware's primary focus is on software development and engineering services across different industry verticals and segments. Our core expertise can be classified into these 7 to 8 categories that you see on the slide, starting with platforms and compilers, frameworks and tools, sensor and video engineering, embedded systems, data engineering, applications and algorithms, process safety and compliance. On the right side, you see some of our customer logos. With that, let's move on to the today's topic, that is, covering some of the fundamental approaches that multi-core follows for optimizing neural network operations or pipelines for the target accelerators. So, who are our target audience for this webinar? If you are someone building your own custom AI accelerator, and if you're looking for software partners to hand optimize or hand tune neural network operations or numerical libraries for your architecture, or if you're planning to add support for end-to-end AI model inference or training, or if you're looking to port software or algorithms from one architecture to another, then this webinar might serve as a starting point to get to know about what we do as a company and engage with us on partnering and to get your requirements fulfilled. In general, we have the expertise in hand tuning and optimizing various computer vision and numerical algorithms for different target platforms, including CPUs, GPUs, DSPs, and AI accelerators. To spend a few minutes explaining why do we think hand optimization is important and how it is useful. So the diagram on the right side shows a typical neural network execution ecosystem, starting with machine learning frameworks on the top like TensorFlow, Caffe, and PyTorch. So when we train a deep neural network model using these frameworks, they are compiled using machine learning compilers like MLIR, TVM, and GLOW, and different nodes in the graphs are mapped to some hand optimized kernels that are present in these libraries that are highlighted in the red box in this diagram, that are hand tuned for each of the specific vendors before the binary is generated. So the compilers in the stack definitely plays an important role in generating optimized code. But every vendor has hand-tuned vendor numerical libraries, and why this is important because of the customization. Every hardware platform has unique architectures and characteristics that makes them more efficient at certain type of computations. So when we hand tune the neural network libraries or numerical libraries in general, we can fully leverage these hardware specific features and instructions in the ISA to get better performance. And next is about the performance improvement that we get, right? Since when we hand tune the numerical libraries, we can fully utilize the hardware specific features, and we can try to reduce the redundant computations involved and increase the parallelism wherever possible. And this obviously results in faster processing times and improved overall performance. And next is about saving the energy. So since there is a performance improvement with hand optimization, the energy consumption can also be reduced, resulting in more efficient use of the resources available, and it certainly lowers the cost. So next is about the competitive advantage that each of these vendors get because of their hand-tuned numerical libraries. These libraries can give these hardware vendors a competitive advantage over others in the market. So by providing their customer with these software libraries that are tailored to these specific hardware platforms, vendor can definitely differentiate themselves and attract more customers who require high performance computing solutions. So these are some of the reasons that we think hand optimization is important. And in the next few slides, I'll talk about some of the basic and fundamental steps in going about optimizing algorithms for the target architecture. So the very first step in optimizing any algorithm for target architecture is to understanding the architecture thoroughly. Um, I've just taken Vision P6, Cadence Tensilica P6 DSP architecture to illustrate what different components to look out for before the engineers deep dive into hands-on optimization. So again, this is just for an example, but similar components may also be applicable for any target accelerator. Yeah, so some of the important components in P6 are, the VPUs, the vector processing units. Understanding the capabilities and functionalities of VPUs is important because they enable parallel processing and vectorization techniques, which can significantly enhance the algorithm performance. And next main components to look out for in any architecture is the memory subsystems. It's important to understand the various subsystems available as part of the memory, including instruction cache, data cache, scratch pad, and data memory. Um, we should try to understand the sizes and characteristics of these components that will enable efficient data access and management. So next is about the local data memory. So for example, P6 architecture does not have a data cache. Instead, it utilizes two local data memory units along with IDM engine. So again, getting to know about these components also help in optimizing data movement and utilization. And the P6 also provides an optional vector floating point units. This enables flexibility when engineers want to do floating point operations on certain algorithms. So next is about understanding the vector register files and other files. For example, the P6 has 32 vector register files and 4 accumulator register files and some predicate register files. Utilizing these registers efficiently can also enhance the algorithm performance and resource utilization. So next is about load and store components. So the P6 architecture includes a load store engine and a super gather engine. So understanding these components can also help in optimizing data movement and accessing the data from different memory locations efficiently. So these are some of the components to look out for in any architecture before deep dive into hands-on optimization. So the next step is, having the functional implementation of the target algorithm. So this diagram shows a typical application development flow. Starting with doing some analysis and research about the algorithm, having the prototype done, and then having the actual functional implementation of the algorithm. Sometimes we call this as a reference implementation for our optimization. Then we go about optimizing the code for the target system, and then we go for porting. So yeah, so having the functional implementation is always helpful because that will serve as a baseline, implementation for us to be able to do the performance optimization. And once the reference or the functional implementation is ready, we should also do the profiling just to identify which portion of the code is consuming a lot of time so that the engineers can focus on those hotspots so to get maximum impact out of the performance. And with the functional implementation we can also identify computational and memory requirements before we deep dive into algorithm optimization. The next step is understanding the ISA. So, understanding the instruction set architecture is also an important step after gaining the knowledge about the processor architecture. Again, I'm taking Vision P6 as an example to delve into important aspects of the ISA. AI processors often provide support for data parallelism, which allows performing the same operations on multiple data elements simultaneously. It is important to understand the SIMD capability of the processor. So next is about having the familiarity with the supported data format. So these formats may include int8, int16, FP16, FP32, etc. So understanding the available data formats helps in determining the appropriate data representation and precision required for different algorithmic computations. Next is about registers, specifically vector registers. So they play a crucial role in SIMD operation. So it is necessary to understand the number of vector register files and the characteristics of these register files available in the processor architecture. Next is about having the knowledge of arithmetic and logical operations supported by ISA. This includes understanding operations like load and store, multiply, accumulate for matrix calculation, move and select, etc. So by understanding these aspects of ISA, the developers can make informed decisions when optimizing algorithms for specific processes. So it is worth noting that while the example used here is for P6, similar concepts and consideration can be applied to other accelerator architectures as well. The fourth step in optimizing the algorithm for the target architecture is to do a theoretical performance estimation. where we try to predict the algorithm's performance on the target architecture depending on the number of computation involved in the algorithm and also the available resources in the target architecture. And doing this estimate is helpful in a lot of different ways. One is it serves as a reference performance benchmark against which the optimized pipeline's performance is compared. And it is useful in identifying the potential design flaws and optimize the design even before the algorithm is implemented. And the next thing is it helps the researchers and engineers in understanding the fundamental limitation of the algorithm. And it also helps when you have multiple solutions for the same problem. Based on the performance estimate, one can compare and select between different alternatives for the given task. So how do we do the performance estimation? As I said, it really depends on the number of computation involved in the algorithm and also the available resources on the target architecture. So for VLIW architecture, the performance estimation involves considering specific metrics, for example, the number of vector operations required and the number of VLIW slots available. So I've just taken a simple example to describe how the estimation is done for an inner loop in an algorithm. So let's say the algorithm requires to multiply and accumulate operations in the inner loop and also 7 ALUs. This is just for an example. And assume the architecture has 5 VLIW slots, and out of which the first one can perform multiply and accumulate operations or ALUs, and the rest two can perform ALU operations. So given this scenario, the total of 9 operations can be completed in 3 cycles, um, depending on the algorithms, specific operation and their dependencies. So yeah, so by leveraging the performance estimation, the developers can get insights into the algorithm's efficiency and optimize it before the implementation, understand its limitation, and make informed decisions when comparing alternative approaches. The next and the important step is actually doing the optimization for the target software on the target device. There are various approaches that one can follow to leverage the full potential of the target device and to achieve the maximum throughput out of the optimization. I've listed some of the maybe more popular optimization techniques here. We can certainly add many more techniques depending on what architectures we're targeting for. So just to brief about each of these techniques, starting with data layout optimization, which basically involves reorganizing the data structures in memory to take advantage of the memory hierarchy in the processor. And by ensuring that the data is stored in a way that minimizes the memory access latency, the algorithm can be made to run more efficiently on the target processor. The next one is instruction selection. The choice of instruction used to implement an algorithm can have significant impact on its performance. And by selecting the instructions that are well suited for the target processor's architecture, the algorithm can be optimized for maximum performance. And the next and the more popular optimization technique is loop optimization, because loops are a common construct in many algorithms, and optimizing them can lead to significant performance gains. Techniques such as loop unrolling, loop fusion, and loop tiling can be used to minimize the loop overhead and maximize the cache utilization. And the next technique is parallelization. Many processors have multiple cores or other parallel computing resources, and algorithms can be hand optimized to take advantage of these parallel resources. Techniques such as multi-threading, SIMD vectorization, and other acceleration techniques can be used to kind of parallelize the algorithm and improve its performance. The next technique is cache optimization. I think the use of caches can greatly improve the performance of any algorithm. Techniques such as cache blocking and cache prefetching can be used to, optimize the use of caches and improve the overall performance of an algorithm. So these are some of the techniques. As I said, certainly we can add many more techniques, for any given architecture. So once these optimization techniques is applied to an algorithm and it is optimized, the next step is obviously to do an evaluation to see whether the results are matching and whether the performance is as expected. So once the implementation is done, the performance of an algorithm is compared against the baseline performance, and so the optimization process is going to be an iterative process, and it is continued until the performance is close to the theoretical estimation that we did in one of our earlier steps. Yeah, so overall, achieving the maximum performance while hand optimizing algorithms for any given target architecture, it definitely requires deeper understanding of the algorithm and the understanding of the target processor architecture and a combination of different optimization techniques. And by using these techniques, it is possible to significantly improve the performance of any given algorithm on a specific hardware platform. So having discussed the fundamental approaches that we follow for optimizing software for the given architecture, why should one choose multi-coreware? It's because we have the more than a decade of experience working in heterogeneous programming and architecture-aware algorithm optimization. We also have experience working with multiple novel architectures in the past and with different optimization. So we have experience in profiling, performance analysis, and optimization of various workloads. And we have the strong expertise in computer vision and deep learning technologies. And we can easily build a strong engineering team for you in a short span of time. And we have the ability to independently work on creating handcrafted numerical libraries for you to achieve high performance and also to enable support for end-to-end model inference. On the right side shows some of the segments that we are targeting with our experience and expertise. And if you need help in any of these target segments, feel free to contact us. Thank you everyone for joining this webinar today. I hope you found this webinar useful. If you have any questions, feel free to post them on the QA window. I think it is open and I'll be answering them one by one. Thank you.
Thank you very much, Nadia, for the presentation. It was well thoroughly explained. So now let us move on to the question and answer session. For the question and answer session, I'd like to welcome Nadia and as well Vinod Kannan, Vice President and General Manager of Compute BU from Multicoreware. Hi, Vinod.
Hi, Srinivas. Hello, friends.
Hi, how are you? Yes.
I'm doing good. Thank you.
So if the audience has any questions, you may pose it in the chat box and we can answer these questions for you. Yeah, so now we have a question, anonymous. What is your development environment like when you hand optimize NN operators or pipeline for a hardware? So maybe Nadia can answer this question.
In terms of development environment, yeah, we primarily work on hardware simulators, most likely with a cycle accurate simulator. And then once we ensure the functionality of an operator or pipeline is correct in the simulator, then we transition the code to the actual device and we test it there. So yeah, we have experience working in both simulators and the actual hardware as well.
Speaking of, we have another question here. So which machine learning frameworks is Multicoreware familiar with? So if you can.
Yeah, I think we have worked with PyTorch, TensorFlow, and ONNX frameworks. I think we have experience working in all of them, and it really depends on what the customer's requirement is. Some of them they prefer to have PyTorch as their supported framework for their inference and training. Some will just choose TensorFlow. So it really depends on the customer's requirement.
Sure, absolutely. Thank you. And Vinod, we have another question here. Have you worked with any architecture where the compute is closer to memory?
Yes, definitely. We have experience working with architectures which implement the in-memory compute. These architectures, right? They are like designed with compute units which is in close proximity to the memory units, which enables efficient data processing. And these kind of architectures also, right, it decreases the memory bandwidth load.
Thank you, Vinod. So another question we have is, yeah, have you worked on adding support for any of the larger models available?
Yes, we have done it in the past, and it's also being done at the present. So we have successfully added support for various large models such as Inception Unit, YOLO, as well as the language-based models such as BERT, and as well as GPT. Our experience includes optimizing these models for efficient execution on various types of AML accelerators.
Right. Yeah. So thank you very much, Vinod. So we have another question. So what is hand optimization? So this is a question from the chat box itself. So Nadia, if you could give us short and sweet, what exactly is hand optimization?
Yeah, it's a process of actually manually you go and optimize some of the software that you have if you want to achieve better performance, or if you want to achieve efficiency, right? So you make changes in the low level code sometimes, or you do algorithmic changes. So sometimes when you write code in, let's say in the high level language like C or Python, right, and it may not run efficiently on your target device, for example, x86. So in that case, you go and hand optimize that specific module or software using intrinsics. Basically, here you are dealing with a low-level language because it gives you more control to access the hardware capability. So you make changes in the assembly or intrinsics level. Basically, you go and touch the low level as well, but it's not only with respect to low level, but you can also do algorithmic modification. Someone can write, naive code, and you can always look at the way to, optimize the design of the algorithm. So basically go and do optimization by hand tuning some of this algorithm when you really want to achieve better performance.
Yeah, thank you very much, Nadia. We also have another question anonymously. So the question is how to handle GPU streams in an ML environment. So he explains, or he or she explains, that most of the ML models itself uses a lot of GPU resources. So even though we hand optimize the kernels, data loader parts, due to the model requirements, the overall performance might not improve. So this user has experienced cases where the GPU streams created within our permissible count and hand optimized kernels in data loader is faster, but the overall E2E time has not improved all that much. So he or she is asking to share some suggestions on this.
Okay. So I think the person is asking that, the ML models are taking a lot of GPU resources. But I think, so whatever we are talking about here is the different layers that are present in the machine learning models. But I think there are some limitations with respect to the machine learning frameworks itself on how they handle the data and pass it through the inference. So I feel there are some limitations in the framework. For example, if you use TensorFlow, the earlier versions we had, like it uses more memory. But I think the optimization that we are talking about is somewhat low level. For example, when you run ResNet or MobileNet or YOLO, so by hand optimizing some of the core layers, you are ensuring that all the basic layer implementations are fully optimized. Right. Yeah, I think there are some works going on as well, just to optimize the data loader part, pre-processing and post-processing. I think yeah, if you take care of the end-to-end pipeline, I think that will certainly improve the performance.
And also like one more aspect I would suggest that the person can check or maybe like look into is the memory bandwidth usage, right? So if the memory is being trashed between CPU, the host CPU as well as GPU, right? Maybe that's one reason where cycles are getting wasted. So that's also something which one can look at if the memory is ready to be processed.
Thank you very much, Nadia and Vinod. So we have another very interesting question. If I might, what would you say about the complexity of hand optimizing OPs for an LLM like ChatGPT? So how would you go about it?
Yeah, so these models are like really heavy. So first of all, we have to look for opportunities to maybe reduce the model size itself. So we can try. First of all, we should try to avoid the redundant computation in the model graph, and then we can see if we can kind of quantize the model, and if there are any opportunities to prune the model, right? So you prune the weights that are maybe less sensitive to the model results. So you can try all these techniques to see if you can first of all reduce the model size itself. So once you try all these techniques, I think you can obviously explore the model parallelism or data parallelism, right? So the data parallelism is basically when you try to distribute the data processing across multiple devices or processors, so you can improve the throughput that way. And so as Vinod said, sometimes the memory will have some limitations, so you should try to reduce the memory footprint when you're processing the model or when you're doing inference for the model. So you should also try to see if you can avoid the unnecessary data transfers, and you should try to reuse the buffers as much as possible. And if you are using any data structures, you should see if you can optimize them. So basically you have to try all these techniques to achieve better performance in case of larger models like GPT models.
Absolutely. Thank you very much, Nadia, for that. So if the audience has any more questions, you can post it in the chat box. And as always, we will be compiling all of the questions and sending it across to all of the registrants here. So if you have any questions, please do let us know in the chat box and we can answer it right away. Yes, so we have another question here. So what kind of software ecosystem is needed for a new AI ML accelerator hardware?
Yeah. I mean, it's a big question. So you really need sort of an SDK that comprises of necessary libraries, the drivers, the compilers, and the runtime component that are specific to the accelerator. So this SDK is generally for the developers to access the hardware's capabilities and optimize the applications. And definitely you need a compiler and runtime. So the compiler will be it is really very specific for this accelerator, and this compiler will take this high level model that someone develops using TensorFlow or PyTorch, and then it basically translates into optimized code. And then, of course, you have to have that integration with the existing ML frameworks. So you need to have that collaboration with either TensorFlow or PyTorch or whatever frameworks that the accelerator company they chooses to develop. And then you need libraries. So as I was talking during the webinar, right? So these libraries will include the optimized implementation of common AI or ML operations. Sometimes we also have data pre-processing algorithms and some specialized algorithms. So yeah, so we need to have all these things, and then of course you need to have some kind of profiling and optimization tools, which will help the developers. So when you're trying to optimize any specific functions, so the profiling would definitely help the developers, analyze the performance bottlenecks and then resource utilization, etc. So You need the SDK, the compiler and runtime, you need the framework integration, you need the libraries, and yeah, of course, to help the developers, you need to have profiling and optimization tools.
Thank you very much, Neha. That was, like you mentioned, quite a big question to answer. So if anyone has any more questions, we can answer it live here, or you can send us your questions and we can collate it and send it to you later. All right. It seems like that is the amount of questions that we have. So thank you very much, Vinod and Nadia, for being a part of the question and answer session. We will be, of course, as I mentioned before, collating all of the questions as well as the recording of the webinar itself, and we will be sending it to all of the registrants present here in a few days' time. With that, we have come to the end of today's webinar. Once again, thank you all of you for joining us today for your active participation. We hope you found this webinar informative and insightful. Have a wonderful night and day ahead, and we're looking forward to seeing you in one of our future webinars once again. Thank you very much and take care of yourselves.